All right, so this is the specific heat formula. We're going to work significantly with this today, and tomorrow we're going to look at the mathematical application of actually plugging numbers in and solving for different variables within this. We did do a triangle, so hopefully if you did not get this triangle, please make sure you write this down. Let me back this up. So here and here we had Q equals M, and then CP, and then delta T. So just based off what you see on the slide that we were just on, what does Q represent? No, what does it represent? The amount of energy transfer. What's its unit? Joules. Okay, what does mass represent? Excuse me. What does M represent? Mass and its unit is grams. Let's do the easy one first. What does delta T represent? Change in temperature, and what does its temperature unit have to be? That's a trick question. It's a trick question. It does not matter. It can be either one. Okay, and then CP is the weird one. A lot of people say, do you have to put that little p? Why does it matter? To me, the reason why I put that little subscript p is because when we get into not the next chapter but the following, there's another variable that is the letter C. And it is only the letter C, and it stands for the speed of light. So I don't want you to get them confused. So, and again, that's the part of science that sometimes can be aggravating, is the same letter represents different things. And so if we can do anything to differentiate between those two, it'll help us out just a little bit. So CP, what does it represent? Specific heat. And its unit, if you were to do it like this, would be joules over gram times which temperature unit? It does not matter. I'm just going to put T for temperature, okay? Whatever temperature unit that we're working with, okay? So what does this mean? What does this matter? What does it have to do with anything in real life? First of all, these tables of specific heats, which value up here has the highest specific heat? Water, okay? You should have learned that number on the calorimetry thing that you guys just did, correct? That number came up a few times. So make sure you know that number because it's definitely going to come into play tomorrow and Wednesday, Wednesday and Thursday, and then Friday, okay? So what is this thing? Up here, I want you to write this. This is called a BOMB, B-O-M-B, calorimeter. And here's what this thing is used for. This thing is used to determine the number of calories in a substance. Now, when I say calories, what's the first thing that pops into your brain? Food. So we could take a banana. We could take a Cheeto. We could take a Snickers bar. And we can put it inside of this thing and determine the amount of calories that it has. Now, what is a calorie? It's a unit of energy. Very good. So what we're trying to determine is how much energy that thing, that food product, or it could be other stuff, gives off. So let's pretend that it's an apple. Okay, so let's just have a square piece of apple that's in there. So what is this outside kind of lighter gray color thing? What does insulating mean? It keeps the heat in, okay? What's this aqua-ish color right in here? Okay, very good. This is the water, okay? What's this little red thing? The stir. What's this purpley looking thing? Thermometer. Do me a favor. Where is the thermometer located? Write that down. That is going to be very, 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 very important to you over the next few minutes and the next few days. The thermometer is in the water. A few days ago, now it's been a while since we've talked about this, we talked about two words. We talked about the system and we talked about the surrounding. Okay? So out beside this, you can write this. What is the system representing? Reaction. So in this particular example, if we're talking about an apple, that's going to be our reaction. We're basically trying to burn an apple to figure out how many calories it releases. What was the opposite of the surroundings? Anybody remember? Excuse me. What was the opposite of the system? Thank you. The surroundings. Now, what does the surroundings include? Everything. So, in this, so we can really say everything else. I apologize about Beautiful handwriting there. So we're looking at two things. We're looking at the system, and we're looking at the surroundings. So in this particular case, what would the water be? Would it be the system, or would it be the surrounding? Very good. So the water is going to be your surroundings. And again, that's important for us to kind of understand this. All right, let's keep deciphering what's going on in here. All right, what's this darker blue colored box? Say steel bomb. Now let me ask you something. Why is it steel? Okay, I'll take that. Will steel heat up? Yes. Okay. So this little yellow thing says a reactant in a sample cup. So again, we can pretend that we've got a piece of apple sitting right here. And what are these little black wires running in here? Ignition, which means it's going to do what? It's going to start it up, it's going to set it on fire. So you can, like I said, it can be a Cheeto, it can be a Big Mac, it can be a Snickers bar, whatever you want it to be. And when we begin to burn that thing, it's going to release energy. What's the first thing that's going to absorb that energy? The steel box. Okay? And what's that steel bomb going to do when it absorbs that energy? Is it going to absorb the heat? Okay? It's going to absorb it. And then, where's the heat going to go from the steel bomb? Into the water. And what's this thermometer going to do when that steel bomb heats up? It's going to go up. So when we're measuring the temperature, are you measuring the temperature specifically of that apple? You're measuring the temperature of what? The water. So this is what I need you to write underneath this. The Q of the water is equal to negative Q of the reaction. Can anyone explain that to me based on what we just talked about? Anybody want to give it a shot? At this point, there's no right or wrong answer. I'm just... Okay, what's another way to say that? It's blank, but it's equal, but opposite. Does that make sense? So, the amount of energy the water has is equal, but what? Opposite to the reaction, because here's the part. What's that apple doing? Is it releasing energy or absorbing energy? It's releasing it. Who's there to absorb it? The water. Does that make sense? So if the apple is constantly releasing energy, what's going to be there to absorb that energy? The water. So does it make sense why it's equal but opposite? Okay. Another way to think about this is if you think about what Q is equal to. mCp delta T. And you don't have to write this down, I just want to talk about it. You just told me that what are we measuring the temperature change of? Are we measuring the temperature change of the water? So, would it be very important that we use the specific heat of the water? Well, if we're using the temperature of the water and the specific heat of the water, should we also use the mass of the water? Would that make sense? Well then, duh, what's left? What Q are we solving for? The Q of the water. Well, here's the problem. What am I trying to find the calories of? The apple. How in the world, if I'm taking the temperature of the water, the specific heat of the water, and the mass of the water, how am I supposed to know what the apple did? You tell how much heat it gave off by how much heat the water absorbed. So it's equal but opposite. Now, is this perfect? No, because is some of that steel box going to take some of the energy out of it? It's not perfect, but it's a very good estimate of what it is. Okay? So this right here is one of the things that I think that you need to understand. So when we do our calculations, this is what we're calculating. That's the numbers you're calculating. But this is my answer. So anytime I ask you for the answer, what's it going to be from your calculation? The opposite sign. Mentally, does that kind of make sense? And I promise you, by the time we're finished with this today, there is something in your notes that's going to make this all click. It's going to make it all make sense. Now, here's the problem. In real life, on Thursday, we don't have one of these big fancy things. They're way too expensive, and they're way too much to have on this level. So we have something like this. We have coffee cups. Now, I get it. That's totally not cool, but it's the best we can do. So this is called a coffee cup calorimeter. If you look at it, is it kind of similar in a very cheap way? A little bit. We've got a thermometer, we've got a stir, and we've got our solution in here. The same exact concept occurs. We're going to be doing the exact same thing in the other one. This one just isn't as fancy. It's not as accurate. So my first question is, notice we've got 2 coffee cups and it's double insulated. Why would we want to use 2 coffee cups? Would it insulate it a little better? Would there be less energy lost to the environment? Yeah, we want to keep as much energy trapped in as we could. Also, oops, that's the wrong button. Do you think that this is important? What happens if you didn't have a cover over it? It would leave, right? So it's a cheap version, but it's efficient. So in terms of air, is this going to have more air than that steel box would be? Yeah, but again, it'll give us enough data that we can work with. Yes, sir. That's the second coffee cup. So like it's where it's sitting down, it's the gap between the 2 cups. Ours will probably fit snug, so there won't be a gap, but it just depends on the cup. And again, it's nothing overly expensive or exciting, but it does do what we need it to do. All right, this is the part where everyone kind of like, I don't understand. The wheels on the bus kind of fall off. But I promise you, after this slide is where it all kind of comes back together. This is where the next slide's where it's going to be running down the road. So just a second ago, you told me that we are dealing with the temperature change of what? Of water. So we needed to use the specific heat of what? Water. And we needed to use the mass of what? Water. And so the Q is going to be the Q of water. Now, let's talk about the signs of all these variables. So we've got Q, M, Cp, delta T. The first one's very easy. Can you have a negative mass? That makes absolutely no sense, right? There's no such thing as a negative mass in our universe. So do you agree that the M will always be positive? Another fact you don't know, but it's just one to just stick in there. Cp will never be negative. Okay, it's always going to be positive. So what are we doing to M times Cp? We're multiplying. So what's a positive times a positive? All right, so this part's always going to be positive. Well, this is where it can be a little bit different. What does it mean for delta T to be positive? What does that mean? What happens to your temperature? It goes up. So is that warmer or cooler? It's warmer. I said hot or cold. So think about this. What is a positive times a positive times a positive? Positive. So that means that energy was... Do you agree with that? If it's positive, that means the water absorbed energy. Well, let's think about that for just a second. Does that make sense? If I hand you a Red Bull, is that going to increase your energy? If I warm you up, is that going to make energy be absorbed? That's how it warms up, right? Okay. Now, the opposite. What happens if the delta T goes down? Do you agree that's cooler or cold? All right, well, what's a positive times a negative? A negative. Okay. Well, we've already established that when it's negative, energy is what? Released. Well, if you're standing outside on a freezing cold day and all your warmth goes out, what happens to your body? You get cold. Does that make sense? This is why this is weird. If you look at these two things, absorbed versus hot, that's kind of backwards from what we talked about in the past. We've always said that when it releases energy, it gets warm. Well, how does this happen? That's because of this bottom thing. The only thing that can tell you whether a reaction is exothermic or endothermic is this thing. What is delta H? Change in what? What is H? Enthalpy. And what is enthalpy? See, you all remember it. Okay? So here's what delta H is. It's exactly what we just said. That delta H of the reaction is equal but what? Opposite to the Q of the solution. If it makes you feel any better, you can write the word H2O beside or above solution. It's the same concept. Same exact concept. So instead of saying that Q of the water is equal to negative of Q of the reaction, you can change it to, instead of Q, you can change it to what variable? Delta H. And again, this is where I said people get a little confused, but this next slide is what pulls it all back together. Draw a big, huge circle around this slide. If you will read this slide, everything will come together. Everything will come together. This is very important. Mason, you with me? You sure? Okay. You don't even have these notes out. You don't even have these notes out. Okay. So let's start with the top row. It says delta T up. What does that mean? If the temperature goes up, right? So if you look at a thermometer and it goes up, do you agree that gets warmer? Okay. How do you get warm in terms of energy? Do you absorb it? Yes. Well, if your Q is positive, we've already established that how are Q and H related? Equal but, well, if Q is positive, then delta H is negative. Well, if delta H is negative, then that's what type of reaction? Exothermic. And what happens to bonds at an exothermic reaction? Bonds are formed and energy is released. Does that help? One sentence that explains all of the things together. If your temperature goes up, it gets warmer, your Q is positive, so your delta H is equal but opposite, so it's negative. A negative delta H is exothermic, so bonds are formed and energy is released. Okay? Let's look at the opposite. What happens if your temperature goes down? It gets cold. Well, that means Q is what? Negative. Well, delta H is equal but opposite, so it's positive. And a positive delta H is endothermic. And what happens in endothermic reaction? Bonds are broken and energy is absorbed. Does that make sense? There's one typo on your notes. Y'all see it? You need to find that on yours. It says bonds are formed. I forgot to change it. Please scratch that out and change it to broken. There is one typo on there. Mason, do you have these? Do you have these? Okay. So, but where is energy released and absorbed from? Okay. It goes and comes from and into the surroundings. That's why you can have a temperature change. And finally, what is allowing you to measure all of this temperature change? What device do you need? A thermometer. Okay, that's the device that you need to be able to do all of this. Okay. All right. Any questions on that? So, like I said, I really think if you guys will commit to that slide, it's really going to help you mentally attach all of these things together. Okay. All right. So, the specific heat problems, let me pass those out.